Good afternoon, everyone. Welcome to our talk. Thank you, everyone, for sticking to the last second topic. And this is about some vulnerability research in classical topics. So a little about us. My name is JunTao. You can just call me Dao. I'm a security researcher at Certic, and I have founded the Travel team, which likes to explore new things. I have been selected into sensing and Huawei owner mobile security hardware free 3 times. At the same time, I have submitted some vulnerabilities to Google and other beneficiaries. Now I mainly focus on mobile and Web3. And this is my partner, Hangyu, and he is a security researcher at Human Cyber. And he is also the co-founder of the Travel team. He mainly focuses on the low-level security research. So here is the agenda. The content mainly revolves around the forgotten trash, focusing on the vulnerabilities that are often overlooked by security engineers and can not easily detected by tools. And I have divided the content into 3 parts. So let's take a first look at why forgotten trashes appear. Here is a little background. So we once had a doubt, is this one of the reasons why wild exploitation continues to appear? If you are familiar with the news about Web3 security vulnerabilities, you should know that if there are problems in the project, it is very easy to cause direct economic losses. Therefore, the audit habit of Web3 project is to find all the vulnerabilities as much as possible. However, the differences between the Web2 project and the Web3 project is that its size is very large, and it is almost impossible to guarantee that all vulnerabilities are discovered. Therefore, some have been tested by tools, of course, that have been manually audited many times, are often ignored. This is the first vulnerabilities in the wild that I want to talk about. That it is very special because many security researchers have noticed and retreated it. The reason for this appears in 3 types that have been tested and audited many times, and because there are many projects using 3 types, so it has a very wild impact. The vulnerability exists in the load spider PNG and which who process the PNG images embedded in fonts. This function first will obtain the image width and the height from the head as 32 bytes integers, and then it truncates the obtained values to 16 bytes and stores them in the T-bit measure structure. And then it will use the truncated values to calculate the bitmap size. Then it will allocate the backing stores of that size. You can see it finally passed the PNG structure and the backing store to the PNG function. So normally this isn't a vulnerability that is difficult to find, but why didn't the fuzzer find it at that time? From the fuzzing test results, you can see that the black box fuzz tools and the fuzzers corresponding to the OSS fuzz platform were used to test this code repository, but the bucket file isn't being fuzzing at all. So that is very clear gap. And the next, let's turn our attention back to the recent vulnerability. This vulnerability appears in the relevant fuzzing code of WebP. It occurred in September last year. It is also the vulnerability in the wild affects the security of Android, Chrome, macOS, and other platforms. The cause of its vulnerability is the problem of the out-of-bounds writing in the implementation of Kaufman coding algorithm. In the processing flow, the decoder first reads the prefixed encoded date from the image date string and builds a completed Huffman encoding table based on this date. Then the decoder will decode the compressed date in the data string according to the table and restore the original image. According to the standard Huffman coding algorithm, when constructing the Huffman coding table, the first level table will be used, and this table is used to carry Huffman codes with a length less than n bytes, and the default bytes is 8 bytes. If the length exceeds n bytes encoding, the decoder will allocate a secondary table to carry this part of long encoding. So the problem is that the Huffman coding table date saved in the decoder's default picture is reasonable. So it calculates the maximum memory length in advance based on this assumption. The core premise here is that the encoding data must conform to the specific of parametric Huffman coding. That is, the Huffman tree should be a complete binary tree with each left node corresponding to a prefix code. There are no unused handling left nodes. However, since the Huffman coding table data comes from the unchecked source and may be arbitrarily controlled by attacker, the decoder passed a completed binary tree without checking the validates of this data and may allocate too much the secondary table and will cause the total memory usage to exceed the pre-allocated size and the heap buffer will close. So regarding the key point of this vulnerability, we can actually focus on two main lines. The first is the count area, and the second is the root table. So here is the count area, which stores the numbers of the users of each line of the code. Specifically, the code length is allocated space in the top-level function, read Huffman code and obtain the corresponding specific date in Huffman code length. This root table is actually Huffman table, and its boundaries are determined at the beginning. So the most important things here is the table size can have user control color cache bytes variables to affect the selection of the fixed values. And the Huffman tables are located using the number hit tree groups times the table size times the size of Huffman tables as the final size. So most of which cannot be changed by the adapter. And the patch here is actually the initial version. In fact, the repair method adopted by Google is to add some new structures for preparation and verification. But the repair on iOS is close to the original version. It can be seen the most direct fix here is to check whether the access element has crossed the boundary. If so, it will fail and return. However, this fix may not particularly perfect, so they later adopt a more complex fix patch. And since LabWebP is also a project in Google OSS Fuzz platform, let's take a look at why this vulnerability was discovered by researchers. We can see that the function file where the problems occurs has actually been relatively fully tested by code coverage. Each function has been 100% covered. So where does the problem lie? Here we need to reflect why hadn't this bug been found earlier? Why had the library not been found enough? Had it not been found right? In fact, the deep-seated reasons why this vulnerability hadn't been discovered are as follows. First is checker connections are very complex. You need to overflow data of sufficient length to track a crash. But in the actual environment, the space allocated by the malloc is usually larger than the actual parameter size passed in. And secondly, the tracking of this vulnerability also requires the corroboration of the first level table and the specific of the encoding data. Thus caused an out-of-bounds problem during the log transversal. And this is the last vulnerability. This vulnerability is located in the TCP URP model. There are some protocols in the Linux kernel that support this model. And these protocols that support this model need to implement TCP URP ops structure, which contain a clone function point. When the TCP three-way handshake protocol is complete, that is, when the TCP listener states change to TCP established, SK clone lock will be called to generate new SK. When the protocol we use, such as subflow, implements the clone function will be called to process the context state. If there is no original sock, it will copy its own context to the new sock. So for example, the TLS protocol doesn't implement this clone. This will result into two different sockets pointing to the same context, which is a typical double-free problem. The interesting point of this vulnerability is that the TLS protocol only allows the TCP established step to be set after the three-way handshake is successful. So we need to use the same sock to repeatedly perform the three-way handshake to check this vulnerability, which always violates the general passcode coverage security. Next, let's turn our attention to the second part, review the targets.
We can see that since Google offers a bounty for Linux, a large number of exploitable vulnerabilities in Linux kernel has appeared. Hangyu also has Ubuntu LT projects every year, so Linux seems to be a great target for bug. As we all know, the most common solution for bug hunting is fuzzing. So we want to fuzz Linux. So first of all, the attack server. A year or two ago, EPF was very famous and had many vulnerabilities, but due to Ubuntu setting, unprivileged user couldn't access this module. You can see the screenshot on my computer here. Next is IOU. Last year at Black Hat, it clearly shows that LUMI had many vulnerabilities and most of them are exploitable. These vulnerabilities could even be used in Android kernel before, but recently Android disabled unprivileged user for accessing LUMI. However, many distributions like Ubuntu allow its use. Therefore, it's a good attack server with repeat code updates. However, the disadvantages are also reversed. Too many people have read it, which makes the vulnerabilities easy to repeat. And then there is our superstar, NetFilter. We can see that a larger number of vulnerabilities in Google KCTF come from this module. We can even see that most of them, looking back at the vulnerabilities in recent years, this module has always been a hotspot for bug hunting. This fully provides that this module is complete enough and may contain a lot of charges. Moreover, a large number of well-known security researchers have published their own charges hunting articles for this module, which makes it very easy for us to get started. But the price is that this makes the vulnerability you find in NetFilter will be easy to repeat, even higher than the LURI. By the way, as a larger number of Linux kernel vulnerabilities are discovered, the price of Ubuntu and Hangyu is decreasing year by year. So, what is the target of fuzzing? After some searching, I finally decided to fuzzing the network package scheduler. Its advantages are it's complete and has no privileges requirement, and most important, it has less attention. Its disadvantages are also reverse. It has poor generalizabilities and require a new namespace. So, how to use NetSchedule? First, we need to create an FD, then call send message with AFLplusplus. There also have a lot of RTM for us to choose. You can choose create new QDs, new class, new chains, new filters, and new actions. RTM new QDs has many options like schedule FIFO, which means first in, first out, and schedule HTTP, schedule multi-queue. RTM net filters also have many options. But first we need to select which CLS you want, like CLS-U32, CLS-follow, CLS-flowers, and then EM, like EM.text, EM.mpt, EM-U32. RTM new actions is the same. You can choose the actions you want. So, after clarifying these structures, it's easy for us to start fuzzing. Like you can use the syzkaller. Unfortunately, after a while, we didn't have any good results. So I decided to do code reviewing directly. Then I find something interesting. Let's look at the CLS flowers. We can see that the FLC's general OPT has arrows in structure that directly using the learn parameter, which look like a potential vulnerability. The length of this arrow is 255. But when we continue to look at it, our subsequent code actually checks the length of length. So this isn't a bug. My spec science told me I should go back and take another look. Let's go back and take a look. We can see that after getting OPT from the arrow, OPT is assigned a value immediately. And below the arrow is the length. And data length will be 0 when we first call this function. And R1, R2, R3 are also 0. So it looks like 0 is off by 1. The arrow contains the OPT struct and the date. Length points to the end of the date field in the arrow. It's not difficult to concentrate a suitable length, and then OPT overrides length to 0. Then we can bypass the check for length and fill the subsequent date into the structure and to complete the out-of-bound right in the structure. The limitation is that we can only overflow 128 bytes. If we look for this structure in the source code, we can see that the structure where our arrow is located is actually combined in two different structures, one of which happens to have a chain that can be overwritten later, which means that we can modify a head point, which can easily convert this vulnerability. The other contains a function point, which means we can modify and read a function point. Since CLS flower provides us with the function of passing the date we pass the bank to user space. It mainly depends on the OPT of each handler and the total length. If we continue to fill data in this error after triggering the structure overflow, since our length has been modified, we will start writing the content of the data again. After layout, we can modify the length of part of original OPT. At the same time, build a fake OPT struct at the end of the error. Then the kernel will mistakenly think that there will be more data passed in later. Thereby, realizing out-of-boundary in structures and links the function point mentioned earlier. And then we success exploited the Ubuntu. And more detail can be found in the link below.
Now let's turn our attention to mobile RCE and the fuzzing logic of HIF. HIF files are special cases of ISO-based media file formats. And it is conditions and timed media and metadata string forms a check, whereas the static media and metadata is stored as items. Consequently, HIF has the following basic dividers. First is the still images are stored as items. And the second, the image sequences are stored as checks. So a file may contain both image items and image sequences checks along with other media. So the picture on the right illustrated how a file player processes the coded image and the derived image include a file. The file player decodes a coded image into a reconstruct image similarly, and the file player applies to the operation of the derived image to the indicated one or more important image to obtain the respective reconstruct image. So the flow chart here simply shows the parsing process of symbol sensing. Since the HIF I mentioned before can actually be regarded as convenient type of file, this is mainly divided into two parts. The first part is about the HIF file head parsing, and the other part is about the parsing of the file content inside HIF. So since the file content is highly inclusive, its content will lead to parsing of some other file formats. So at that time, tools like AFLplusplus hadn't not yet introduced fuzzing tests that could be directly run on mobile phones. So I initially wondered whether I can test these function libraries through the kernel. But this idea was quickly rejected me because the Gen 9 interface elements of these function libraries are relatively complex Java objects, which may not be well suitable for the simulation testing kernel. So I considered whether I could use Frida to write a fuzzer for completed code coverage calculation. So here it is, a not too bad fuzzer. Its main improvement is that it doesn't hook multiply functions through JS, but directly use the function interface brought by the Frida core. In fact, the Frida core itself is that underlying hooking framework directed through the G object. So we can directly use its underlying interface. The function shown in the pictures here, the on message will transmit the code block information checked by the underlying stacker back to our harness program, and thereby realizing the collection of block coverage and some other functions will support some crash or excess signals. So the final effect is that I can run my fuzzer directly on my phone. The results of fuzzing test is totally 60 vulnerabilities were discovered within months, including 5 critical and 1 high. And the CB 2021-39804 is actually a bit interesting. This vulnerability itself, it is not very dangerous, but it does bring me some inspiration and encouragement, which proves platforms like OSS Bus cannot achieve 100% success, even if faced with some parsing modules. that can have been tested many times. Different fuzz testing methods will still be able to discover different security vulnerabilities. So let's compare some existing fuzzing test tool methods, which are basically continued from the last year, DERCON 2023. The MJ, he wrote a great series of blogs. The Blank, he had a research about the closed source Android binary fuzzing, and I used to write the Frida fuzzer. The Pokes and have a topic about Android J9 fuzzing, and the guys from Zhejiang University also test some sensing closed source libraries. So fuzzing testing has been a general approach to find the bugs in closed source native libraries. For mobile testing targets, code coverage should be the most effective fuzzing testing methods. From an object point of view, currently in Android native level, basically all the function libraries objects can be fuzz tested. For shared library, if the parameters are memory address or object, string, file description, we can use the QMU to collect the code coverage. If the parameters are object of Java level, we can use JVM or QMU or Frida to collect the code coverage, such as a service process, and there is already a corresponding tools like Chapsify, and its implementation parameter is also to collect the code coverage through the Frida. And for native network process and the session, Netella from the Google Project Zero did the corresponding fuzzing test on some mainstream information transmitting software, including the WhatsApp and other applications. So the method used was also similar to the Frida passive fuzzing test. So in theory, it can also use Frida to collect the code coverage. So is there anything else we should pay attention to? As we mentioned before, the CBE 2020 999 is missed by fuzzing test operations, and the CBE 2023 4863, they are missed because of complex conditionals and deep tracker paths. Another point is that the seed source of fuzzing test always affects some aspect. Sometimes it is difficult for us to find the seed files that can trigger deep level code very accurately. So in addition, fuzzing testing tools themselves usually have various problems. For example, the Frida is very unstable and prone to crash in the actual usage several times, and its testing speed is very slow. And due to the particular of mobile Frida code coverage crashing, the multi-line process parallel fuzzing test method is also very difficult to implement. So it's time to review, and here is the CB 2023 30699. In fact, this isn't a very complex type of vulnerability. It's still happening in the header parsing module that appears in the HIF file. So why hadn't this bug been found by fuzz? So here is the details about CB 2023 30699, and the V338 variable will store the file data read from the HIF, and it will use as the size in the subsequent read function. And V21 points to a memory area, and its header stores the value of 1, and it will plus 1 from the V21 as the memory read area. So since we can control this important length, it seems out of bounds override, but there is a limitation that the sum of the length is actually the same as the elements accumulated in the malloc parameter object before. So this will have to be no problem. Actually, the real problem is here. There is an integral truncation vulnerability, which can cause malloc to allocate less space than expected. You can see that in assembly code, this vulnerability uses the AND instruction instead of the move instruction. So its overlogic is as shown in here. it will traverse the collection area in HBCC function, and then will traverse the nail unites inside each area, and calculate the final space size that need to be collocated based on the size of each nail unite plus the length of the prefix. Therefore, due to the previous integral truncation vulnerability, an out-of-bounds write problem will occur here. So why is this vulnerability doesn't find by fuzzer? It is the vulnerability that also requires multi-line connection to match. This parsing part is a submodel in the head, and it requires that the heap file has multi-line nails. But in fact, the value of each nail is limited in the small size. And finally, the sum of these values must exceed the maximum value of unint 32. So next, let's turn our attention to the content of three-part, enhance our fuzzers. So why fuzzer fails? The first kind is that the modules of the vulnerability is difficult to construct. For example, some memory destructive vulnerabilities may not have inbuilt effects such as crashes. So when they write out of bounds, they may perform at the internal of some memory unites, and the modified values is reasonable under certain probability. And the second situation is usually more common in some closed-source fast cases, because in some cases the trigger paths of the code are many and complex. It is difficult to determine all the key process modules in a short time. Therefore, in most cases, more attention may be paid to the earlier processing modules. There is also the third type of the vulnerability, which is often the hardest one to find. It needs to be triggered when the multi-line conditions are met at the same time. In many cases, we may not actually understand the key points involved in parsing a function. At the same time, in closed parsing tests, we usually focus more on the adaptation of earlier interface parameters and the improvement of the code coverage. And in addition, there are still some type vulnerabilities are difficult to find with the fuzzing test. So we improved our fuzzing in the following ways. First, for multi-line layer nest structures, we pay more attention to the efficiency of the fuzz testing to reach specific blocks or instructions rather than the code coverage. This means we may pay more attention to the depth of the code testing rather just than the breadth. Because many existing fuzzing test tools focus on the breadth, but some test results or vulnerabilities only occurred in the shadow code. Frequently, crashes in the shadow logic are not very contactive to test the deep code. And secondly, we pay more attention to the part testing of some key instruction locations. For example, we use multi-line test on the same path, and we use the different or unique values based. So in general, this is the guided fuzz testing structure that focus more on some forgotten vulnerabilities. And here are some new vulnerabilities we discovered. We can find that we can still find some new vulnerabilities on these targets. However, since some vulnerabilities are still being fixed, we will mainly talk about the latest kernel here.
So the bug is in schedule multi-queue. The multi-queue init the queues and make them invalid with a no queue disk. The length of the queen is determined by number TX queen. We can see that at position 1, QOPT bands are assigned. Then at position 2, removed is allocated by Qmax bytes minus Q bytes. At position 3, Q bytes is assigned by QOPT bytes, At position 4, we put some arbitrary choices of objects into the remove arrow, and then freeze them at position 5. Why is the old Q bind used to allocate the remove size at the position 2, but the new Q bind is used in the for loop later? This seems strange. If max bind minus the new bind is greater than twice max bind minus the old bind, the for loop may write out of bind to a head point that will be freed soon. But first, we need to figure out what number TX queens and the real number TX queens are. After I check it to the source code, ask AI, and try it in my own network card, I found this to require the hardware support. So this is a useless part. My span size tells me things are not that simple. What if we create a virtual network card? Boom. We can now control the real number TX queens, and the default number TX queens is 128. Here's an example. First, we create a network card. Then we set real number TX queens to 124. Call molecule twins again, which will create a 124th valued object. Then modify the real number TX queens to 190. Call molecule twins again. We can write a head point auto bound that will be released immediately. So the vulnerability was fixed by us a few weeks ago, and there is a demo.
Thank you.